Hello, let's go over this probability question. I think overall this probability question I did relatively well on because it was pretty standardized, I'd say. In part A, we're asked for each of the following functions, decide whether it is a valid probability density function for some value of alpha, and if so, find the value of alpha and also the expectation of the corresponding random variable. So in part I, we have this, right? So for any kind of checking if it's a valid PDF, there's kind of two main conditions that we need to test. The first is that f of x is greater than or equal to 0 for all x, as well as the fact that if we do something from negative infinity to infinity of the integral, then it should equal to 1. So what we can do is, okay, so in part I, we have was a function alpha 2 times x minus x squared for x from 0 to 2. So for this, we know that, okay, from this, from 0 to 2, f of x is greater than or equal to for all x. So, and then the condition is that alpha has to be greater than 0. So then we can just take the integral and find the area of that. And then taking the integral, we get that. And then moving from that, it's just basic algebra. And we equate it to 1. So then we find that alpha is equal to this, which would give basically a valid PDF. And then we're asked to find the expectation of this. So the expectation would be just the integral from 0 to 2 because we're in that range, right? Everything else is 0, so it wouldn't matter. X times P of x equals x. Plug it into here, solve the integral, and we get that the expectation is also equal to 1. So we're done for this part. For the second part, we have this equation. Basically, from x squared, we'll change to x cubed. When we check this, we automatically see a problem because, okay, if I just expand this out, right, it would be something of this form. So in the case that, let's say for x equals square root 3, then we have a problem because it's negative, it evaluates negative, which fails the first condition that fx has to be greater or equal to 0 in all of the ranges. So it's not a valid PDF. So yeah, we're done with part A, second part. And let's move on to BI. This gives us a condition that the random variable V be uniformly distributed on the interval A to B. Find the constants D and D such that CV plus D uniformly distributed on 0, 1. Justify your answer. Okay, so how I thought about this question was, okay, I know that it's this one and I'm trying to fit it to 0 to 1, right? What is C and D? So I know the interval of A to B is B minus A because let's just say that B was the bigger number. So then I know that the interval of from 0 to 1 is 1. So I need to scale the A to B interval to 1. So that means that my C has to be 1 divided by B minus A. And then this would mean that basically now I scaled it to this is a mistake, I would say. This part was a mistake. So it's not actually this. Basically, I would just do this. So then the A would be A or times divided by B minus A to B divided by B minus A. And then to get this to 0, 1, yeah, basically this part is not right. This is not legit. So to get this to 0, 1, I would need my C to be this, and my D would be negative A divided by B minus A. This is because if I multiply 1 over B minus A to my A, then would it have been A divided by B minus A, right? And then the other part, the B part would have been um, B divided by B minus A. So both of these I would require, basically my D would need to get this to 0. So this would just be what I subtract, so hence that would be my D. So that would be a sufficient explanation. But a more formal way of doing that would be taking the following approach. So basically I know that V is follows the uniform distribution from here, right? The uniform distribution, this CDF of that would be of this form, V minus A divided by B minus A for a V between A and B. So what I'm trying to do is I'm just going to define W to be equal to CV plus D, and this follows a uniform distribution from 0 to 1. So yeah, I'm trying to find this. I'm just going to do a strictly linear transformation, assuming C is greater than 0. Basically, this would be the definition of CDF for W, right? This is for any kind of variable. We would do that. We substitute W for its definition of CV plus D. And then we just move every term over and we get this. This would just be f of v, right? And we just know that from here, f of v was equal to this thing, v minus a divided by b minus a. So we just plug this directly into this equation, simplify it so that we get this. We know that it has to equal w, right? For 0, 1, it's w, so it's going to equal w. So then we're just going to put whatever's w coefficient and then whatever this is equal to w. By just matching coefficient, I know that C1 divided by C times B minus A is equal to 1. So C is 1 divided by B minus A. And then on this term over here would be 0 because there's nothing over here, right? So it would just be 0. So then I just rearrange it. I substitute what my C is, and I get that D is equal to this. So yeah, I get the same result, but doing it a bit more formally with CDF, I'd say. And moving on to part two, let U be uniformly distributed on 0, 1, find the CDF and PDF of U squared. Okay, so U squared would just be kind of slightly changing it up using CDF and then finding what we have for PDF, right? So the idea for these questions is always pretty straightforward. We go from a distribution that we know, um, kind of change it up with the CDF, see what the CDF is for that, and then finally take the derivative to get the PDF. So yeah, our CDF would be the following: f of u of x is equal to fu smaller than or equal to x. So then, or inside here for uniform, it would just be x. So for fu squared of x, it would just be u squared smaller than x. And that would mean that u is smaller than square root of x. And since it's positive, we're kind of good, right? So it's just square root of x. So then what we have is that because it's from 0 to 1, we're still good in the range. So nothing changes over here. It's still the same. And then since it's CDF, yeah, basically it's 0, square root x up to this point, and then 1 afterwards. So this function would look something like this. PDF would just be the derivative of the CDF. So we just take this, pretty straightforward. 0, 0, constants, not much to say. This one, just square root x, taking the derivative of that. So yeah, we get this, 0 otherwise. Part C, we're asked, suppose that the continuous random variable x has probability density function. This thing over here, 1 over 2x, if it's 0 to 2, otherwise 0. Let y be x times 2 minus x. Calculate py greater than y, and hence find the PDF of y. Okay, so this is what we have, right? This is our x function, y is equal to this. So we're trying to find this. If we're trying to find this, that means that we can just substitute the big Y in terms of X, right, directly by the definition. And then we would just rearrange this, and we would get this. So by our quadratic equation, we know that X is either 1 plus square root 1 minus Y or 1 minus square root of that thing. So then we would just know that based on just analyzing which part is smaller than 0, we know that, okay, this is a upward facing parabola. So that means that the region that's actually below the x-axis would be the one in the middle. So yeah, that's why x is in between these two roots. And then from there, we know that, okay, if we have this, right, we just take these as the boundary cases and then take the integral of this, f of x, because we know what f of x is. So hence, what we have is 1 over 2 and then we have the first thing minus the second thing, and then we would get square root of 1 minus y. And from here, what we have is, okay, if we have this thing, right, py greater than y. So then for the CDF, it would be py smaller than or equal to y. So this is just complementary counting, and it would just be 1 minus that part, right? So it would just be 1 minus of this answer over here. So then from here, once I know the CDF, PDF's very straightforward. I just take the derivative of this. And yeah, I forgot to take 1 over 2 from here. Yeah. But the idea is that this would be the final kind of PDF. So then our final PDF would just be f of y from either this thing over here that we just found from 0 to 1 or 0 otherwise. Why is it from 0 to 1? Because we can kind of just go back to our original function, right? Where was the function? I am Okay, so here, our function is 1 over 2x. And then our y is x times 2 minus x. So let's say that like this is basically like a parabola, right? And then we know that the minimum value would be 0 because when we plug in 0, it would be 0 times something, which would be 0. When we do 2, it's also a root, so it's also at 0. And then we know that this parabola is symmetric and upward facing. And the maximum value is at 1, where x equals 1, then y equals 1. So hence we know that's between 0 and 1 for those. And the boundary is not included. So over here, I made a mistake. It should have been 0 smaller than 0 is not possible, but 1 is possible because 1 is included. So the range should have been 0 smaller than y, smaller than or equal to 1. So then over here, it would have been this. Should have been the PDF. So yeah, basically, this question really comes down to, do you know the conditions for PDF, right? PDF just mainly has two conditions, like the greater than or equal to 0 at all points, and then the integral of the thing equals to 1. I think those are the two main conditions that we need to be concerned about. And for part B and part C, it's just mainly testing, okay, the idea is no matter what you have of some kind of variable, you substitute that variable away, and then from there you would try to get the CDF of the thing, and then from CDF you can take the derivative to get the PDF. So yeah, that's the idea behind part C. Sorry, my handwriting is not very good here. But yeah, you get the idea. That's sort of what's being tested over here.